There are places in the universe where the rules change, places where time bends, where space itself folds inward, where light cannot escape. These places are called black holes, and if you were to fall into one, your journey would be unlike anything else in existence. Let us begin somewhere quiet, somewhere far from Earth, floating in the darkness of space. Around you, stars shine in every direction. Some are close, some are impossibly distant. The universe stretches out in all directions, vast and silent. But there is something else out here, something you cannot see. Ahead of you, the stars begin to look strange. They bend. They curve around an invisible point, as if space itself is pulling them sideways. Some stars seem to circle endlessly, trapped in an eternal dance around nothing at all. This is your first hint. You are approaching a black hole. What exactly is a black hole? The simplest answer is this. A black hole is a place where gravity has become so strong that nothing can escape it. Not rocks, not gas, not even light itself. Light is the fastest thing in the universe. It travels at 300 million meters every single second, and yet, near a black hole, even light cannot break free. This tells us something remarkable. Whatever lies at the heart of a black hole must have gravity stronger than anything else we know. To understand how this happens, we need to think about gravity itself. Gravity is a force that pulls things together. The Earth pulls you toward its center. That is why you stay on the ground. The Sun pulls the Earth, keeping our planet in orbit. Every object with mass creates gravity. The more mass something has, the stronger its gravity. The Sun has much more mass than Earth, so its gravity is much stronger. If you stood on the surface of the Sun, which you could not because it is made of hot gas, you would weigh about 28 times what you weigh on Earth. But even the Sun's gravity is gentle compared to what we are about to explore. Now imagine this. Take all the mass of the Sun, all of it, but instead of spreading it out across a sphere nearly 1.5 million kilometers wide, squeeze it down. Smaller, smaller still. Squeeze it into the size of a city, then a mountain, then a house. Keep going. Compress all that mass into a space smaller than a marble. What happens? The gravity becomes extraordinary, unimaginable, so powerful that it tears space and time themselves. This is how a black hole is born. In reality, black holes form in a specific way. They come from dying stars. Most stars live for billions of years, burning fuel at their core. This fuel creates heat and light and an outward pressure that pushes against gravity. The star is balanced. Gravity pulls inward. Pressure pushes outward. The two forces hold each other in check, but eventually every star runs out of fuel. When a very massive star, at least 8 times heavier than our Sun, uses up all its fuel, something dramatic happens. The outward pressure vanishes. Gravity wins. The star collapses inward in an instant. The core of the star is crushed down, smaller and smaller, until all its matter is packed into an impossibly tiny space. Sometimes this collapse creates a neutron star, an object so dense that a single teaspoon of its material would weigh as much as a mountain. But if the star is massive enough, the collapse does not stop. It keeps going. The core shrinks past the neutron star stage. It becomes smaller than an atom, smaller than anything we can measure. At the center, all the matter collapses into a single point. Scientists call this point a singularity. Around that singularity, space itself bends so steeply that it creates a trap, a boundary. Once anything crosses this boundary, it can never return. This boundary is called the event horizon, and together, the singularity and the event horizon, these form a black hole. The collapse happens in silence. No sound travels through space. There is only the sudden disappearance of a star replaced by an invisible monster lurking in the dark. The black hole does not glow. It does not shine. It simply pulls. From a distance, you would not see the black hole itself. You would see its effects. You would see light bending around it, stars orbiting an empty point, gas and dust spiraling inward, glowing brightly as they fall, heating up from friction before they vanish forever. But the black hole itself? Invisible. Not all black holes are the same. They come in different sizes. The smallest black holes are called stellar black holes. These form from individual dying stars. They might weigh anywhere from a few times the mass of the Sun to perhaps 100 times the Sun's mass. Their event horizons are relatively small, just a few kilometers across. Then there are intermediate black holes. These are larger, weighing hundreds or thousands of times the mass of the Sun. Scientists are still learning how these form. They may result from many stars collapsing together or from smaller black holes merging over time. And then there are the giants. At the centers of most galaxies, including our own Milky Way, there exist supermassive black holes. These monsters weigh millions or even billions of times the mass of the Sun. Our galaxy's supermassive black hole is called Sagittarius A. It sits at the very heart of the Milky Way, about 26,000 light-years from Earth. It weighs approximately 4 million times as much as the Sun. Despite this enormous mass, Sagittarius A is surprisingly quiet most of the time. It does not devour stars constantly. It simply waits, pulling in gas and dust slowly, a patient giant at the center of our cosmic home. So now we return to our imagined journey. You are floating in space, approaching a black hole. Let us say it is a stellar black hole formed from a single massive star. It weighs about 10 times the mass of the Sun. At first, nothing seems unusual. You drift forward slowly. The stars around you look normal. Space feels like space. But as you move closer, things begin to change. The stars ahead of you start to shift. Their positions seem wrong. Light from distant stars bends as it passes near the black hole, curving around the intense gravity. This bending of light is called gravitational lensing. It creates a strange effect. The black hole acts like a lens, warping the view of everything behind it. Stars that should be hidden appear to curve around the edges. Some stars seem duplicated, appearing in two places at once, and directly ahead, where the black hole sits, there is a perfect circle of darkness, a shadow. The event horizon is still far away, but the black hole's gravity is already bending light so strongly that no light can reach you from that direction. This dark circle grows larger as you approach. Let us pause here and talk about the event horizon. The event horizon is not a physical surface. It is not made of anything solid. You could not touch it. There is no wall, no barrier, no membrane. Instead, the event horizon is a boundary in space itself. It marks the point of no return. Imagine you are rowing a boat on a river. Upstream, you can row against the current and make progress. But as you approach a waterfall, the current becomes stronger. Eventually, you reach a point where the current is so powerful that no amount of rowing can save you. You will be swept over the edge. The event horizon is like that point on the river. Once you cross it, every direction you could possibly travel leads inward. There is no path that leads back out, not because you lack the strength, but because the geometry of space itself has changed. All roads lead down, even if you could somehow travel at the speed of light, which nothing with mass can do, you still could not escape. The event horizon is the place where even light gets trapped. The size of the event horizon depends on the black hole's mass. The more massive the black hole, the larger the event horizon. For our 10 solar mass black hole, the event horizon would be about 60 kilometers across. That is roughly the size of a large city. For Sagittarius A Calc, the supermassive black hole at the center of our galaxy, the event horizon is much larger, about 24 million kilometers across. That is nearly 17 times the diameter of the Sun. This size difference matters for something we will discuss soon. Larger black holes have gentler gravity at their event horizons. Smaller black holes have fiercer gravity. This will become important when we talk about what happens to your body. You continue drifting closer. The circle of darkness grows. It fills more and more of your view. The stars around it bend and shimmer, distorted by the warping of space. And now something very strange begins to happen. Time starts to change. This might sound impossible. Time feels constant to us. 1 second passes, then another, then another. Clocks tick at the same rate whether you are on Earth, on the Moon, or anywhere else. But this is not quite true. Time is not as fixed as it seems. According to Einstein's theory of general relativity, gravity affects time itself. Near a very strong gravitational field, time runs slower. Imagine you have a clock with you as you approach the black hole, and imagine your friend is watching from a safe distance, far from the black hole, with their own identical clock. At first, both clocks tick at the same rate, 1 second per second. But as you drift closer to the black hole, your friend notices something odd. Your clock starts to tick more slowly. Not from your perspective. To you, it still ticks normally, but to your friend watching from far away, each tick takes longer. This effect is called time dilation. The closer you get to the black hole, the more extreme this becomes. When you are very near the event horizon, your clock might tick once while your friend's clock ticks 100 times, or 1,000 times, or 1,000,000 times. From your friend's perspective, you appear to move in slow motion. Your arm moves slowly. Your chest rises and falls with each breath, but each breath seems to take minutes, then hours, and then something even stranger happens. As you approach the event horizon itself, time dilation becomes infinite. To your distant friend, you seem to slow down more and more until you appear to freeze completely, hovering just above the event horizon. They watch you get closer and closer, but you never quite seem to cross. You just hang there, motionless, trapped at the edge forever. This is not an illusion. From your friend's frame of reference, you genuinely never cross the horizon. Time for you, as seen from the outside, has stretched out infinitely. You are frozen at the boundary, and you will appear that way for eternity. But here is the remarkable thing. From your perspective, nothing strange happens at all. You do not slow down. You do not freeze. You cross the event horizon smoothly in a finite amount of time. Perhaps it takes you 10 seconds, perhaps 30, but you cross. You and your friend experience the same event in completely different ways. To them, you never fall in. To you, you do. Both perspectives are correct. Time itself is relative. This creates a profound mystery. If someone watching from outside never sees you cross the horizon, what does it mean to say that you fell in? The answer lies in the nature of observation. Your friend cannot see what happens to you once you cross, because no light or information can escape from inside the event horizon to reach them. They see you frozen at the edge because the last light rays that left your body before you crossed are stretched out over infinite time. But you, the person falling in, continue to exist. You continue to experience time. You move forward. The universe does not stop just because someone far away can no longer see you. This is one of the deep truths of relativity. There is no single universal now. Different observers experience time differently, and near a black hole, these differences become dramatic. Let us return to your journey. You are now very close to the event horizon. From your perspective, time flows normally. You can think, you can breathe, you can look around. What do you see? Behind you, the universe looks strange. The stars are blue shifted, their light compressed, shifted toward blue and violet. This is because you are falling into the gravitational field, and light waves are squeezed together as they reach you. Ahead of you, the darkness is absolute. The event horizon is invisible, but you know it is there. Beyond it lies the interior of the black hole, a place from which no information returns. And then you cross. The moment of crossing is not dramatic. There is no flash of light, no sound, no sudden jolt. According to the equations of general relativity, the event horizon is smooth. You pass through it just as you would pass through an invisible plane in empty space. You might not even notice the exact moment it happens. But once you have crossed, something fundamental has changed. Every direction you could now travel leads toward the singularity. There is no path back. The singularity is not just in front of you, it is in your future. No matter what you do, no matter which direction you try to move, time itself will carry you forward to that point. It is as if time and space have traded roles. Outside the black hole, you can move freely through space, but time always flows forward. Inside the black hole, you can move freely through time, but space always leads inward. The singularity is not a place you will reach, it is a moment in time you will inevitably arrive at. And now, as you fall deeper inside, gravity begins to do something terrible to your body. This is the part of the journey that is not gentle. This is where the physics becomes harsh. As you fall inward, you feel gravity pulling on you. But the pull is not even. Your feet are closer to the singularity than your head. The difference might only be 2 meters, the height of a person, but that difference matters. At this distance, the gravitational pull on your feet is stronger than the pull on your head. This difference is called a tidal force. We experience tidal forces on Earth, though they are very weak. The moon's gravity pulls on the side of the Earth facing it slightly more than the side facing away. This creates the ocean tides, pulling water into bulges. Near a black hole, tidal forces are not gentle, they are extreme. The difference in gravity between your head and your feet begins to stretch you. At first, it is a light pulling sensation, uncomfortable, like being on a rack. But as you fall closer to the singularity, the stretching becomes stronger, and stronger still. Your legs are pulled harder than your torso. Your torso is pulled harder than your chest. Your chest is pulled harder than your neck. Every part of you is being pulled at a slightly different rate. You begin to elongate. Your body stretches vertically. At the same time, the black hole's gravity squeezes you from the sides, compressing you horizontally. You are being turned into a long, thin thread. Physicists have a name for this process. They call it spaghettification. Spaghettification is exactly what it sounds like. You are stretched like a piece of spaghetti, longer and thinner, until you are no longer recognizable as a human being. You become a stream of atoms, a thin ribbon of matter spiraling inward toward the singularity. Stephen Hawking described this vividly. He said that an astronaut falling into a black hole would be stretched like spaghetti. It is a strangely gentle way to describe something so violent. How quickly this happens depends on the size of the black hole. For a small stellar black hole, spaghettification would begin before you even reach the event horizon. The tidal forces would rip you apart while you were still outside, shredding you into a stream of particles before you crossed the boundary. But for a supermassive black hole, the experience is different. These giants are so large that their tidal forces at the event horizon are relatively gentle. You could cross the horizon intact. You could survive inside the black hole for a while, falling inward, still alive, still conscious. But not forever. Even in a supermassive black hole, the tidal forces grow stronger as you fall deeper. The singularity waits at the center, and as you approach it, the stretching becomes inevitable. Eventually, even in the gentlest black hole, spaghettification will find you. There is no escape. The singularity is your future, and it is a place where all distances shrink to zero, where gravity becomes infinite, where the equations of physics break down and give nonsensical answers. We do not know what truly happens at the singularity. Our best theories, Einstein's relativity and quantum mechanics, both fail there. They cannot describe what it means for space and time to collapse into a single point. Perhaps the singularity is not really a point. Perhaps something else happens, something we do not yet understand. But from the outside, it does not matter. Nothing that reaches the singularity can ever send information back. The singularity is hidden behind the event horizon, sealed away from the rest of the universe. Let us pause here for a moment. We have traveled far already. We have approached the black hole. We have crossed the event horizon. We have felt the beginning of spaghettification, the stretching that pulls us toward the singularity. But there is more to this story, much more. There are mysteries hidden in the physics of black holes, questions about what happens to information, ideas about whether black holes might connect to other places, theories about what an outside observer would truly see, and there are real black holes out there in the universe, waiting in the darkness, each one a puzzle we are still trying to solve. We have crossed the event horizon. We have felt the pull of gravity beginning to stretch us. But our journey into the black hole is far from over. There are stranger things waiting ahead. Things that challenge everything we think we know about reality. Let us continue deeper. Before we fall any further, let us step back for a moment. Let us return to the outside universe and ask a different question. What would someone watching from a safe distance actually see? Imagine your friend again, floating far from the black hole in a spaceship. They have a powerful telescope pointed at you. They are watching your descent. From their perspective, remember, time near the black hole runs slower. As you approach the event horizon, they saw you move in slow motion. Your movements became sluggish. each second of your time stretched into minutes of theirs, then hours, then years. But there is something else happening too, something visual. As you fell closer to the event horizon, the light, leaving your body, had to work harder and harder to escape the black hole's gravity. This struggle changed the light itself. Light is made of waves. Different colors of light have different wavelengths. Red light has a longer wavelength. Blue light has a shorter wavelength. When light climbs out of a strong gravitational field, it loses energy. As it loses energy, its wavelength stretches. The light shifts toward the red end of the spectrum. Scientists call this gravitational redshift. As you approach the event horizon, the light bouncing off your spacesuit and traveling back to your friend became redder and redder. If you were wearing a blue suit, it would look purple, then red, then deep crimson, then darker still. Eventually the light would shift beyond red into infrared, then into radio waves. The wavelength would stretch so much that your friend's eyes could no longer detect it at all. Combined with the time dilation, you would appear to fade away, growing dimmer, redder, slower, until finally you simply disappeared from view, frozen at the edge of the event horizon, your image fading into the darkness like a ghost. Your friend would never see you cross the horizon, not because you did not cross, but because the light carrying that information can never reach them. The last photons of light that left your body just before you crossed the horizon would take infinitely long to climb back out. They would be stretched across time itself, arriving slower and slower, redder and redder, forever. In a sense, your image would remain at the event horizon eternally, a faint frozen echo of the moment before you fell in. This is one of the strange paradoxes of black holes. From your perspective, you crossed quickly and smoothly. From your friend's perspective, you never crossed at all. You are stuck at the boundary forever. Both views are true. Reality depends on where you are standing. But let us return to your perspective. You have crossed the horizon. You are inside the black hole now. What does it look like in here? This is one of the great unknowns. No one has ever been inside a black hole. No information has ever returned from inside to tell us what is there. Everything we can say is based on mathematics and theory. According to Einstein's equations, the inside of a black hole is still made of space and time, but they are warped in extraordinary ways. Outside the black hole, space extends in all directions. You can move left, right, forward, backward, up, or down. Time flows in one direction only, forward. Inside the black hole, this changes. All directions through space now point toward the singularity. You cannot move away from it any more than you can move backward in time. The singularity is not a place somewhere in front of you. It is a moment in your future that you will inevitably reach. This is hard to picture. Our brains are not built to imagine such warped geometry. Perhaps it helps to think of it this way. Imagine you are floating in a river that flows in all directions. No matter which way you swim, the current carries you downstream. You cannot swim upstream because there is no upstream. Every direction is downstream. The waterfall at the end of the river is not somewhere ahead of you. It is in your future, and the current of time itself carries you toward it. This is what space is like inside a black hole. The singularity is everywhere in space, but nowhere in particular. It is simply ahead of you in time. You fall, not just through space, but through time. The two have become tangled together in ways that make them almost indistinguishable. How much time do you have before you reach the singularity? This depends on the size of the black hole. For a small stellar black hole, the answer is not long, perhaps a few thousandths of a second. You would cross the event horizon and reach the singularity almost instantly. You would not have time to think, not even time to blink. For a supermassive black hole like Sagittarius A, you might have hours, even days. The interior is so vast that you could fall for a long time before reaching the center. During that time, you would still exist. You would still be conscious, at least until the tidal forces grew too strong. You could look around. You could wonder about where you are, but you could not communicate with the outside world. No signal you sent could escape. No radio transmission. No light beam. Nothing. The event horizon is a one-way door. Information can fall in, but it cannot climb back out. As you fall, the stretching continues. The tidal forces grow stronger with every moment. At first, the stretching might be bearable, uncomfortable, but not yet deadly. Your body would feel pulled as if you were being gently stretched on a rack. But the singularity draws closer. The gravity intensifies. The difference between the pull on your feet and the pull on your head becomes enormous. Your bones begin to creak. Your muscles stretch. Your skin pulls taut. And then the structure of your body begins to fail. First, perhaps your legs separate from your torso, not because they are cut, but because the tidal forces simply pull them apart. Then your torso stretches, longer and thinner. Your arms are pulled away. Your neck elongates impossibly. You are no longer a person. You are a string of disconnected parts, each being pulled into a thinner and thinner strand. Eventually, even your cells are torn apart. The molecules that make up your body are stretched. The atoms themselves are pulled into a line. You become a stream of particles, a one-dimensional thread spiraling down toward the singularity. And at the very end, even the atoms are crushed. The electrons are stripped away. The nuclei are compressed. Matter itself breaks down into its most fundamental components. Whatever you were, you are no longer. You have been disassembled by gravity, reduced to elementary particles falling into the heart of the black hole. This is the fate of anything that falls into a black hole. Stars, planets, spaceships, people all meet the same end: stretched, compressed, destroyed, absorbed into the singularity. And yet there is a mystery here, a deep puzzle that physicists have struggled with for decades. What happens to the information? Let me explain what this means. In physics, there is a principle called the conservation of information. It says that information can never be truly destroyed. It can be scrambled, it can be hidden, it can be transformed, but it cannot simply vanish. If you burn a book, the information in the book is not destroyed. It is converted into heat and smoke and ash. In principle, if you knew the exact position and state of every particle in the smoke and ash, you could reconstruct what the book said. The information is scrambled, but it still exists. This principle is fundamental to quantum mechanics, the physics of the very small. Quantum mechanics insists that information is conserved, always. But black holes seem to violate this principle. When you fall into a black hole, you carry information with you. The arrangement of atoms in your body, your memories encoded in the neurons of your brain, every detail about you. That information crosses the event horizon and falls toward the singularity. It is trapped inside. It cannot escape. And then, according to Einstein's theory, it is destroyed at the singularity, crushed out of existence. If this is true, then the information is gone, deleted from the universe, and this would mean that quantum mechanics is wrong. This conflict is called the black hole information paradox. It has puzzled physicists since the 1970s. It suggests that either general relativity is incomplete or quantum mechanics is incomplete, or both. The paradox becomes even stranger when we consider something called Hawking radiation. In 1974, Stephen Hawking made a startling discovery. He found that black holes are not completely black. They actually emit radiation. They glow very faintly, like dying embers. This sounds impossible. How can anything escape from a black hole? The answer lies in quantum mechanics, specifically in something that happens in empty space. Even in a perfect vacuum with nothing around, quantum mechanics says that space is not truly empty. Pairs of particles constantly pop into existence and then annihilate each other almost instantly. These are called virtual particles. An electron and a positron might appear, exist for a tiny fraction of a second, and then collide and disappear. Normally, we never notice these virtual particles. They appear and vanish too quickly to measure. But near the event horizon of a black hole, something strange can happen. Imagine a pair of virtual particles appearing right at the edge of the horizon. One particle appears just inside the horizon. The other appears just outside. The particle inside the horizon is trapped. It falls into the black hole and is lost forever. But the particle outside the horizon is free. It can escape. It flies away into space, carrying energy with it. To an outside observer, it looks as if the black hole has emitted a particle. This is Hawking radiation. But where did the energy come from? It came from the black hole itself. By losing a particle into its interior, the black hole had to give up a tiny amount of mass to create the escaping particle. Einstein told us that mass and energy are equivalent, E equals mc squared. So losing mass means losing energy. The black hole is evaporating, very, very slowly. For a stellar mass black hole, Hawking radiation is incredibly weak. The temperature of the radiation is a tiny fraction of a degree above absolute zero. It would take far longer than the current age of the universe for such a black hole to evaporate completely. For supermassive black holes, the evaporation is even slower. It would take trillions upon trillions of years. But in principle, every black hole will eventually evaporate. Given enough time, it will radiate away all its mass and disappear. And this brings us back to the information paradox. If a black hole eventually evaporates completely, what happens to all the information that fell into it? The Hawking radiation appears to be completely random. It carries no information about what fell in. An electron that escapes as Hawking radiation looks the same, whether it came from a black hole that swallowed a star or a black hole that swallowed a person. So when the black hole finally disappears, the information seems to be gone, deleted from the universe forever. This would violate quantum mechanics. And many physicists believe quantum mechanics is sacred. It cannot be violated. So where is the information? One possible answer is that the information is not lost. It is encoded in the Hawking radiation somehow, in ways we do not yet understand. The radiation only appears random. In reality, it carries subtle correlations that encode everything that ever fell in. But extracting that information would be impossibly difficult, like trying to reconstruct a book from the pattern of heat and smoke particles after it burned. Another possibility is that the information is stored on the event horizon itself. This is a radical idea called the holographic principle. It suggests that everything inside a black hole can be described by information encoded on its surface, on the event horizon. Let me try to explain this strange idea. Normally, when we think about objects, we think of them as three-dimensional. A ball has a volume. A room has volume. To describe everything inside a room, you need to know what is at every point throughout the entire volume. But the holographic principle says something different. It says that all the information about the interior of a region of space can be encoded on the boundary of that region. On the surface, not in the volume, it is called holographic because of holograms. A hologram is a flat, two-dimensional image that contains all the information needed to reconstruct a three-dimensional scene. When you look at a hologram, you see depth, even though the hologram itself is flat. The holographic principle says the universe works the same way. A black hole's interior, three-dimensional space, can be completely described by information on its two-dimensional event horizon. This seems bizarre. How can a volume be described by a surface? Think of it this way. Imagine you are inside a spherical room with mirrors on the walls. If the mirrors are perfect, everything that happens inside the room is reflected on the walls. By looking at the walls, you could, in principle, figure out everything happening in the interior. A black hole's event horizon is similar. Everything that falls in leaves an imprint on the horizon. The horizon records it. The information is not inside the black hole. It is painted on its surface in a scrambled encoded form. This would solve the information paradox. When Hawking radiation escapes, it could carry away the information bit by bit, encoded in subtle correlations. Nothing is truly lost. The holographic principle is not just a wild guess. It comes from serious theoretical work by physicists like Leonard Susskind and Gerard 't Hooft. It has deep connections to string theory and quantum gravity. But it raises strange questions. If the interior of a black hole is just an encoding of information on the surface, does the interior even exist? Or is it an illusion? A hologram projected from the boundary? Some physicists believe the interior is real, others believe it is emergent, arising from the information on the horizon in some way we do not yet fully understand. And this leads to even stranger possibilities. In 2012, a group of physicists proposed something called the firewall paradox. They were trying to reconcile quantum mechanics with the idea that information escapes in Hawking radiation. They discovered a problem. According to their calculations, if information truly escapes and quantum mechanics is preserved, then the event horizon cannot be smooth and empty. Instead, there must be a wall of energy at the horizon, a firewall. If the firewall exists, then you would not cross the event horizon smoothly as we imagined earlier. The moment you touch the horizon, you would be incinerated instantly, burned to ash by a blast of ultra-high energy particles. This contradicts Einstein's principle of equivalence, which says that falling through the event horizon should be no different from falling through empty space. There should be nothing special at the horizon. The firewall paradox created a crisis in theoretical physics. It suggested that we must give up something. Either quantum mechanics is wrong, or general relativity is wrong, or the interior of a black hole does not exist at all. Many physicists rejected the firewall idea. They searched for ways to preserve both quantum mechanics and smooth horizons. Some proposed that black holes might be connected by wormholes to other regions of space, allowing information to escape through hidden tunnels. Others suggested new principles of quantum gravity that we have not yet discovered. The debate continues to this day. No one knows the answer for certain. For our imagined journey, we will assume the firewall does not exist. We will assume you can cross the horizon smoothly, as Einstein predicted. But we must acknowledge that this is not settled science. It is an open question. Let us pause here and consider what we have learned. Black holes are not just objects, they are puzzles, riddles written in the language of mathematics and physics. They challenge our understanding of reality. They sit at the boundary between quantum mechanics and gravity, two theories that do not quite fit together. They force us to ask deep questions about the nature of information, time and space itself. And yet black holes are real. They exist out there in the universe, not as abstract ideas, but as actual objects we can observe and measure. We have detected black holes in many ways. We see them by watching stars orbit around invisible points. We measure the star's velocities and calculate the mass of the object they are orbiting. When that mass is large enough and compact enough, we know it must be a black hole. We see them when they feed. Gas and dust falling toward a black hole form a swirling disk called an accretion disk. The material in the disk rubs against itself, heating up to millions of degrees. It glows brightly in X-rays before it crosses the horizon and disappears. These glowing disks are some of the brightest objects in the universe. We even see them when they collide. When two black holes spiral together and merge, they shake space itself, sending out ripples called gravitational waves. In 2015, scientists detected gravitational waves for the first time, confirming that black holes collide and proving that Einstein's predictions were correct. In 2019, we saw something even more remarkable. Using a network of radio telescopes spread across the entire Earth, scientists created an image of a black hole's shadow. The black hole was at the center of a distant galaxy called M87, 55 million light-years away. It weighs 6.5 billion times the mass of the Sun. The image showed a glowing ring of light surrounding a dark circle. The dark circle is the shadow of the event horizon. The ring is the accretion disk, gas swirling around the black hole at nearly the speed of light, glowing brilliantly just before it falls in. It was the first direct image of a black hole, a picture of the edge of the abyss. Seeing that image felt profound. It was a confirmation that black holes are real, that the mathematics of general relativity, worked out by Einstein over a century ago, truly describes the universe. And in 2022, scientists released a second image, this time of our own galaxy's black hole, Sagittarius A star. Sagittarius A star is much smaller than the black hole in M87, but it is also much closer. Only 26,000 light-years away, at the very heart of the Milky Way. The image looked similar, a glowing ring, a dark center, the shadow of the event horizon. Our galaxy revolves around this object. Hundreds of billions of stars, including our Sun, orbit this supermassive black hole at the center. It is the anchor point, the heart of our cosmic home. And yet, it is silent, invisible, a dark secret hidden at the core. Black holes are everywhere in the universe. There are likely tens of millions of stellar mass black holes in our galaxy alone, the remnants of massive stars that died long ago. Most of them are invisible, drifting quietly through space, detectable only by their gravitational effects. And at the center of nearly every large galaxy, there sits a supermassive black hole, some weigh billions of times the mass of the Sun. These giants may have formed in the early universe, growing over billions of years by consuming gas, dust, and stars. We do not fully understand how supermassive black holes grow so large. Did they start as stellar mass black holes and grow gradually? Or did they form as massive objects right from the beginning, born in the first moments after the Big Bang? These are questions we are still working to answer. There is another type of black hole that scientists predict but have not yet confirmed. Primordial black holes. These would be black holes that formed not from dying stars, but from density fluctuations in the very early universe, just after the Big Bang. If the early universe had regions where matter was packed slightly more densely than average, those regions could have collapsed directly into black holes. Primordial black holes could be any size. Some might be tiny, weighing less than a grain of sand. Others might be much larger. If they exist, they could account for some of the mysterious dark matter that fills the universe, unseen and undetected except by its gravity. But so far, we have no direct evidence of primordial black holes. They remain a theoretical possibility. Let us return now to the journey, to the experience of falling inward. We have talked about what happens to your body, the stretching, the spaghettification, the crushing forces. But what about your mind? What would you think? What would you feel? This is harder to answer. We can calculate the physics of gravity, but we cannot calculate consciousness. We do not know what it feels like to be stretched into a thread or crushed at the singularity. Perhaps there is no feeling at all. Perhaps the tidal forces would disrupt your neurons so quickly that consciousness would simply cease. One moment you are thinking, the next moment you are not. Or perhaps for a brief instant you would feel the pull, a sensation of being torn apart, a moment of awareness before the end. And there is another possibility, a stranger one. What if black holes are not endings at all? What if they are doorways? This is not science yet, it is speculation. But it is speculation that some serious scientists have explored. One idea is that black holes might be connected to white holes. A white hole is the opposite of a black hole. While a black hole only lets things in, a white hole only lets things out. Nothing can enter a white hole. Everything inside is expelled. White holes are solutions to Einstein's equations, just like black holes. But we have never seen one. They may not exist in nature. However, some theories suggest that every black hole might connect to a white hole somewhere else. Perhaps in another part of our universe. Perhaps in another universe entirely. In this picture, falling into a black hole would not mean destruction. It would mean passage. You would fall through a tunnel, called a wormhole, and emerge from a white hole on the other side. Where would you end up? No one knows. Another region of space, another time, another universe with different laws of physics. This is the realm of science fiction, but it is science fiction based on real equations. Wormholes appear naturally in the mathematics of general relativity. Einstein himself, along with physicist Nathan Rosen, discovered them in the 1930s. They called them bridges. But there is a problem. Wormholes, as they appear in the equations, are unstable. They collapse almost instantly. To keep a wormhole open, you would need something with negative energy, a kind of exotic matter that pushes instead of pulls. We do not know if such matter exists. Quantum mechanics hints that it might, in very special circumstances, but we have never observed it. We have never created it. So while wormholes are mathematically possible, we do not know if they are physically real. Still, the idea is tantalizing. The thought that black holes might be gates instead of graves, that they might lead somewhere instead of nowhere. Some physicists have gone even further. They have proposed that our entire universe might exist inside a black hole, that the Big Bang, the explosive beginning of space and time, might actually have been a white hole, the exit point of a black hole in some larger parent universe. In this model, every black hole that forms in our universe could give birth to a new baby universe inside it. These baby universes would be unreachable from ours, separated by the event horizon, but they would be real, expanding and evolving on their own. This creates a kind of cosmic family tree. Universes within universes, nested like Russian dolls, each one born from a black hole in the layer above. It is a beautiful idea, strange and dizzying, but beautiful. Is it true? We do not know. We may never know. These baby universes, if they exist, would be completely cut off from ours. We could never observe them, never communicate with them. But thinking about such possibilities expands our sense of wonder. It reminds us how much we do not know, how many mysteries remain hidden in the fabric of space and time. Black holes are more than just objects that pull things in. They are windows into the unknown. They show us the limits of our understanding and invite us to go further. We have explored the science of black holes, the mathematics, the theories, the paradoxes. But there is another side to this story, a human side. Black holes exist not just in equations, but in our imagination. They have captured our curiosity for decades. They appear in our stories, our films, our dreams of the future. Let us talk about what black holes mean to us, and then let us return to the darkness one more time to explore the strangest possibilities of all. For most of human history, we did not know black holes existed. Ancient people looked up at the night sky and saw stars. They created stories about them, constellations. Gods and heroes painted across the darkness, but they had no concept of gravity warping space, no idea that stars could collapse into invisible monsters. Even when Isaac Newton discovered the laws of gravity in the 1600s, no one imagined black holes. Newton's gravity was powerful enough to explain why planets orbit the sun, but not powerful enough to trap light. It was not until Einstein published his theory of general relativity in 1915 that black holes became possible, at least on paper. Einstein's equations showed that massive objects warp space and time. A few months after Einstein published his theory, a German physicist named Karl Schwarzschild found a solution to Einstein's equations. He discovered that if you compressed enough mass into a small enough space, you would create a region from which nothing could escape. This was the first mathematical description of a black hole. Schwarzschild found it while serving as a soldier in World War I. He sent his calculations to Einstein from the Russian front. Shortly afterward, Schwarzschild died of an illness. Einstein himself did not believe black holes could truly exist in nature. He thought they were mathematical curiosities, strange solutions to the equations that did not correspond to anything real. For decades, most physicists agreed with him. But in the 1930s, a young Indian physicist named Subrahmanyan Chandrasekhar calculated what would happen to a dying star. He discovered that if a star was massive enough, nothing could stop its collapse. It would shrink and shrink until it created what we now call a black hole. Many older scientists rejected his ideas. They thought he must have made a mistake. But Chandrasekhar was right. Slowly, over the following decades, physicists began to accept that black holes were not just mathematical oddities. They were real objects that could form in the universe. The term black hole itself was not coined until 1967 by physicist John Wheeler. Before that, they were called frozen stars or collapsed objects. Wheeler's name stuck because it captured something essential: a hole in space, a pit of darkness that swallows everything. The first real evidence for black holes came in the 1970s. Astronomers discovered a bright X-ray source in the constellation Cygnus, called Cygnus X1. The X-rays were coming from gas spiraling around an invisible object, something massive and compact. A normal star orbited this invisible companion, pulled by its gravity. By measuring the orbit, scientists calculated the mass of the invisible object. It was too heavy to be a neutron star. It had to be something else. It had to be a black hole. Stephen Hawking famously made a bet with physicist Kip Thorne about whether Cygnus X1 was truly a black hole. Hawking bet against it, even though his own research supported black holes. He later said he made the bet as an insurance policy. If black holes turned out not to exist, at least he would win the bet. In 1990, Hawking conceded. The evidence had become overwhelming. Cygnus X1 was a black hole. Since then, we have found thousands of black holes. We have measured them, studied them, watched them devour stars and collide with each other. But we have never been close to one. Every black hole we have observed is thousands or millions of light years away. They are distant objects, far removed from our daily lives. And yet they fascinate us. Why? Perhaps because they represent the ultimate unknown, the ultimate boundary. Black holes are places where the rules break down, where our science reaches its limit, where mysteries remain unsolved. They are cosmic question marks. Black holes also represent power, unimaginable, absolute power. A single supermassive black hole can weigh as much as billions of suns. It can tear apart entire stars. It can swallow planets whole without slowing down. It bends light, stops time, and destroys anything that comes too close. And yet, it does all this silently, invisibly. A black hole does not roar. It does not shine. It simply exists, pulling, waiting. There is something both terrifying and beautiful about that. A force so powerful it needs no display, no announcement. It is the quiet at the center of chaos, the stillness at the heart of the storm. Black holes have inspired countless stories. In science fiction, they are often portals, doorways to other worlds. Ships travel through them to distant galaxies, emerging on the other side unharmed. Sometimes they are time machines, allowing travelers to journey into the past or future. These stories are not based on science, but they touch on real possibilities. Wormholes, white holes, the strange geometry of warped space-time. Other stories treat black holes as threats, cosmic dangers that must be avoided. Ships that venture too close are pulled in, never to return. Civilizations that orbit black holes live on the edge of destruction, one mistake away from annihilation. And sometimes black holes are simply backgrounds, places where the strange becomes normal, where the laws of physics are different, where anything is possible. One of the most famous depictions of a black hole appears in the film Interstellar, released in 2014. The film worked closely with physicist Kip Thorne to create a scientifically accurate visualization of a black hole. They used the equations of general relativity to simulate how light would bend around the black hole's event horizon. The result was stunning. The black hole, called Gargantua, appeared as a dark sphere surrounded by a glowing accretion disk. But the disk did not look flat. Gravity bent the light so strongly that you could see the disk above and below the black hole at the same time. The light wrapped around the black hole's gravity, creating a strange, warped halo. It was the most accurate depiction of a black hole ever created at the time. When the real image of the black hole in M87 was released in 2019, it looked remarkably similar to Gargantua. Science fiction had predicted science fact. Interstellar also explored the time dilation effects near a black hole. In the film, the characters land on a planet orbiting close to Gargantua. Because of the intense gravity, time on that planet runs much slower than time far away. Every hour on the planet equals 7 years back on Earth. This is not fantasy. This is real physics. Time truly does slow down near massive objects. If you orbited close to a black hole and then returned, you would find that much more time had passed for everyone else. You would have travelled into their future. The film showed this with emotional weight. One character returns from the planet to find that decades have passed. His children have grown old. Messages from them have piled up. Years' worth of life he missed while only hours passed for him. This is one of the profound consequences of relativity. Time is not universal. It is personal. It depends on where you are and how fast you are moving, but not all depictions of black holes are accurate. In many films and shows, black holes are shown pulling in everything nearby like cosmic vacuum cleaners. Ships are dragged toward them from great distances, helpless to escape. This is not quite right. Black holes are not cosmic vacuum cleaners. Their gravity is strong, but only near the event horizon. From far away, a black hole's gravity is no different from any other object of the same mass. If the Sun suddenly became a black hole, which it will not because the Sun is not massive enough, the Earth would continue orbiting exactly as before. We would not be pulled in. We would not notice any change in the Sun's gravity. We would only notice that the Sun's light had gone out. Black holes only become inescapable once you cross the event horizon. Until then, you can escape, as long as you have enough speed. Another common misconception is that black holes roam the galaxy, hunting for victims. Most black holes are stationary, or at least moving in predictable orbits. They do not chase anything. They simply sit in place, waiting. If you want to avoid a black hole, simply stay away from it. The nearest known black hole to Earth is about 1,500 light-years away. That is an enormous distance. Light, the fastest thing in the universe, would take 1,500 years to travel from that black hole to us. We are safe. Earth is not in danger of falling into a black hole anytime soon. Not in our lifetimes. Not in millions of lifetimes. But still, we imagine. We wonder, what if? What if one day humanity develops the technology to travel to a black hole? What if we could send a probe close to the event horizon? What could we learn? We could test the laws of physics in the most extreme conditions imaginable. We could measure time dilation directly. We could watch matter spiral into the accretion disk and see how it behaves in such powerful gravity. We might even be able to use black holes as tools. Some scientists have proposed that advanced civilizations could use black holes as power sources. By dropping matter into a black hole, you could extract enormous amounts of energy from the accretion disk. The glowing disk around a feeding black hole is one of the most efficient energy sources in the universe. A sufficiently advanced civilization could build structures around a black hole, capturing this energy. They could power entire worlds from a single black hole. Black holes might even serve as engines. If you could control how matter falls into a black hole, you could in theory use the black hole's gravity to propel a spacecraft. By dropping mass asymmetrically, you could create thrust. The black hole would become a kind of engine, pulling you forward through space. This is purely theoretical. We do not have the technology to capture black holes or manipulate them, but the laws of physics allow it. Perhaps millions of years in the future, our descendants will build cities around black holes. Perhaps they will harvest their energy. Perhaps they will use them as highways through space, traveling through wormholes, if wormholes can be stabilized. Or perhaps black holes will remain untouched, sacred, too dangerous to approach, monuments to the power of gravity and the mystery of the universe. Let us imagine one more journey, one final fall. This time we will not fall into an ordinary black hole. We will fall into the largest black hole we know of. Its name is TON 618. TON 618 is a supermassive black hole at the center of a distant galaxy, about 10 billion light-years from Earth. It weighs 66 billion times the mass of the Sun. It is one of the most massive black holes ever discovered. Its event horizon is so large that light would take more than 2 days to cross from one side to the other. You could fit multiple solar systems inside its event horizon. If you approach this giant, you would barely notice its gravity at first. The tidal forces at the event horizon would be gentle. You could cross the boundary intact, alive, unharmed. You drift toward TON 618 in a small ship. The black hole fills the sky ahead of you, a vast circle of darkness surrounded by a glowing disk of light. The disk is unimaginably bright. Gas and dust falling toward the black hole heat to millions of degrees. The light is so intense it would blind you if you look directly at it. The disk stretches for billions of kilometers, a thin plane of matter spiraling inward at a significant fraction of the speed of light. Jets of particles shoot out from the poles of the black hole, perpendicular to the disk. These jets extend for thousands of light years, blasting through space at nearly the speed of light. They are powered by the black hole's rotation and magnetic fields, channeling energy outward in focused beams. This black hole is not quiet. It is feeding, devouring a galaxy's worth of matter. It is a monster, and you are approaching its jaws. As you draw closer, you begin to feel the pull. Not painful, not yet, just a gentle acceleration. The ship is falling now, pulled by gravity. You cross the event horizon. The moment is unremarkable. No flash, no barrier. You simply pass from outside to inside. Behind you, the universe begins to look strange. Light from distant stars is compressed, blue shifted. The entire universe seems to gather into a bright ring behind you, shrinking as you fall deeper. Ahead of you, there is only darkness. The singularity is somewhere in that darkness, days of travel away. You have time, perhaps 2 days, perhaps 3. Enough time to think, to explore, to record your observations. This is the interior of a black hole. No human has ever been here. No probe has ever sent back data from inside. You are the first, and you will be the last, because no message you send can escape. You look around. What do you see? This is the question that haunts physicists. What does the interior of a black hole look like? Einstein's equations describe the geometry of space-time inside a black hole, but they do not tell us what you would actually see. Light behaves strangely here. The paths it takes are warped by gravity in ways that are difficult to imagine. Some calculations suggest that you might see multiple images of yourself. Light leaving your body could loop around the black hole's interior, returning to your eyes from strange angles. You might see your own back, your own face staring at you from the darkness, or you might see nothing at all, just blackness, the singularity ahead absorbing all light before it can reflect back to you. We do not know. You drift deeper. Hours pass, then a day. You begin to feel the tidal forces now, a slight pulling sensation. Your feet are being tugged harder than your head. The difference is small, but growing. You know what this means. The singularity is approaching. Not in space. It is not a place you can point to, but in time. It is your inevitable future. You check your instruments. Your ship's sensors are trying to measure the space-time around you. The numbers they return are increasingly strange. Curvature values growing, tidal gradients intensifying. Another day passes. The pulling sensation has become uncomfortable. You can feel your spine stretching, your legs ache. The gravity is no longer gentle, and then it happens quickly. The tidal forces surge. Your body is pulled violently. You feel your joints separating, your bones cracking. Pain floods through you for an instant, and then nothing. You are no longer you. You have been stretched beyond the breaking point. Your body has come apart. Your consciousness has ceased. What remains is a stream of particles falling the final distance toward the singularity. And at the singularity, even particles cannot hold together. Space and time compress to infinite density. The matter that was once you is crushed out of existence, or transformed into something else, something we do not have words for. This is the end of the journey. Or is it? Some theories suggest the singularity is not an end, it is a transition. In loop quantum gravity, a branch of theoretical physics, singularities do not exist. Instead, when matter is compressed to the smallest possible scale, called the Planck length, it rebounds. It bounces. In this picture, the singularity is replaced by a bounce. Matter falling into a black hole would compress to an incredibly small size, but not quite to zero. Then it would expand again, creating a new region of space-time. A new universe, perhaps. You would not survive the bounce. You would be disassembled long before reaching that point. But the matter that made you up might pass through. It might become part of a new cosmos, with its own space, time, and physical laws. Another theory, called black hole cosmology, suggests something similar. In this model, every black hole contains a universe. When matter falls into a black hole and reaches the center, it does not hit a singularity. Instead, it passes through a transition and emerges into an expanding universe on the other side. From inside this new universe, the black hole's event horizon would look like a Big Bang, a sudden beginning of space and time. In this view, our own universe might exist inside a black hole. The Big Bang might have been the interior of a black hole forming in some parent universe. And every black hole we see might contain a universe of its own, with galaxies, stars, and perhaps even life. It is a staggering thought, a hierarchy of universes nested within each other, each one born from the collapse of matter in the layer above. These ideas are speculative, We have no way to test them. We cannot look inside a black hole and check. We cannot observe these hypothetical universes. But they emerge from serious attempts to unite general relativity with quantum mechanics. They are not wild fantasies. They are careful explorations of what the mathematics might allow. And they remind us of something important. The universe is stranger than we imagine, and perhaps stranger than we can imagine. Black holes are not just endings. They might be beginnings. They might be doorways. They might be seeds. Let us step back now. Let us return to the familiar universe, to Earth, orbiting a quiet star, far from any black hole. What have we learned from this journey? We have learned that black holes are real. They are not myths or mathematical tricks. They exist, scattered throughout the cosmos. We have seen their shadows. We have felt their gravitational waves. We have watched stars orbit around them. We have learned that black holes challenge our understanding of reality. They force us to confront the limits of our knowledge. They show us where our theories break down and new physics is needed. We have learned that black holes are powerful. They can tear apart stars. They can bend light. They can trap anything that crosses their boundaries. And we have learned that black holes are mysterious. They raise questions we cannot yet answer. What happens to information? What lies at the singularity? Do wormholes exist? Are there universes inside black holes? These mysteries are not frustrating. They are inspiring. They tell us that we do not know everything, that there is more to discover, that the universe still has secrets waiting to be revealed. Every generation of scientists stands on the shoulders of those who came before. Newton built on Galileo, Einstein built on Newton, Hawking built on Einstein, and the next generation will build on Hawking. They will develop new theories, new tools, new ways of probing the universe's mysteries. Perhaps they will solve the information paradox. Perhaps they will unify quantum mechanics with gravity. Perhaps they will find a way to peek inside a black hole without falling in. Or perhaps they will discover that the questions we are asking are the wrong questions, that black holes are even stranger than we thought, that reality works in ways we have not yet imagined. For now, black holes remain at the edge of our understanding. They are signposts marking the boundary between the known and the unknown. And that is beautiful. Science is not about having all the answers. It is about asking better questions. It is about being comfortable with uncertainty while working to reduce it. It is about wonder. Black holes inspire wonder. They invite us to look up at the night sky and think about the invisible monsters lurking between the stars, to contemplate the nature of time and space, to imagine what might lie beyond the edge of reality. If you were to fall into a black hole, you would not survive. That much is certain. The forces would tear you apart. The singularity would crush you. You would be lost to the outside universe, frozen at the event horizon forever from your friend's perspective, but crossing smoothly and falling inward from your own. But in another sense, perhaps you would never truly be lost. If the holographic principle is correct, the information that makes you up would be encoded on the event horizon, scrambled beyond recognition, but still there. And as the black hole slowly evaporates over trillions of years, that information might escape bit by bit in the Hawking radiation. You would be transformed, spread across the cosmos as particles and photons, but you would still exist in some form, woven into the fabric of the universe. And if black hole cosmology is correct, perhaps the matter that made you up would pass through the singularity and emerge into a new universe. Perhaps you would become part of the building blocks of new stars, new planets, new forms of life. In that sense, falling into a black hole would not be an ending. It would be a transformation, a journey from one reality to another. This is speculation, of course, poetry mixed with physics, but it is grounded in real mathematics and real attempts to understand the universe, and it gives us a different way to think about black holes, not as destroyers, but as transformers, not as prisons, but as passages. We have reached the end of the third part of our journey, but there is one more section to come, one more set of mysteries to explore. In the final part, we will look at the biggest questions that remain. We will explore the cutting edge of black hole research. We will talk about what scientists are working on right now and what discoveries might be waiting just over the horizon. We will consider what black holes tell us about the nature of reality itself, about time, space, information, and existence. And we will end with a sense of quiet wonder, standing at the edge of the cosmic abyss, looking into the darkness, knowing that the darkness is looking back. We have travelled far together. We have crossed the event horizon. We have felt the pull of gravity. We have explored the mathematics and the mysteries. Now, in this final part of our journey, let us ask the deepest questions of all. What are black holes trying to tell us about the universe? What secrets do they hold? And what might we discover in the years to come? There is something profound about black holes that goes beyond the physics. They represent a kind of boundary. Not just a boundary in space, but a boundary in understanding. Throughout history, humans have encountered boundaries like this. Places where our knowledge stopped, where the map ended and the unknown began. Ancient sailors looked at the horizon and wondered what lay beyond. They drew maps with edges, marking the unknown waters with warnings. Here be dragons. Astronomers looked through telescopes and saw distant galaxies and wondered what lay beyond those. How far does the universe extend? Does it have an edge? And now we have black holes, the ultimate boundary. Beyond the event horizon lies a region we cannot observe, cannot measure, cannot communicate with. It is the closest thing in the universe to a true edge, a place where here ends and something else begins. But unlike the edges on ancient maps, the edge of a black hole is real. It is not drawn from ignorance or fear. It is a physical boundary, described by mathematics, confirmed by observation. And that makes it even more fascinating. We know the boundary exists. We can calculate exactly where it is. We can measure its size. We can watch things fall across it. But we cannot see what happens on the other side. This is new territory for science. Usually, if we want to know what happens in a particular place, we go there and look. Or we send a probe. Or at least we observe it from a distance. With black holes, none of these options work. The interior is fundamentally hidden from us. Not because our technology is not good enough, but because the laws of physics forbid information from escaping. And yet science continues. We cannot look inside, but we can think about what the interior might be like. We can use mathematics to explore possibilities. We can develop theories and test their predictions. This is how black holes have driven so much progress in theoretical physics. They force us to think carefully about the foundations of reality, about what happens when gravity becomes extreme, about how quantum mechanics and relativity fit together. Every attempt to understand black holes reveals new puzzles, and every puzzle, when solved, opens up new questions. It is an endless frontier. Let us talk about some of the questions scientists are working on right now. One of the biggest mysteries is the information paradox. We talked about this earlier, but let us go deeper. The paradox arises because two fundamental theories disagree about what happens to information. General relativity says that information falling into a black hole is destroyed at the singularity. It is gone forever. The universe has fewer details than it did before. Quantum mechanics says this is impossible. Information cannot be destroyed. It can be scrambled, hidden, transformed, but never erased. The universe must always have the same amount of information. For decades, physicists have tried to resolve this contradiction. Stephen Hawking spent much of his life working on this problem. In the 1970s, he showed that black holes emit radiation and eventually evaporate. But the radiation appeared to be random, carrying no information about what fell in. This suggested that information really was destroyed. Hawking called this the information loss paradox. For 30 years, he argued that information was lost, that quantum mechanics needed to be modified, that black holes were special places where the normal rules did not apply. But in 2004, Hawking changed his mind. He conceded a bet he had made with physicist John Preskill. He announced that he now believed information was preserved after all. What changed his mind? New calculations suggested that the Hawking radiation might not be completely random. It might carry information in subtle correlations between particles. Information escaping so slowly and in such a scrambled form that it seemed random, but was not truly random. Think of it this way. Imagine you burn a book. The book is destroyed. The pages turn to ash and smoke. But in principle, if you knew the exact position and velocity of every atom in the smoke and ash, you could reconstruct the book. The information is there. It is just scrambled beyond recognition. Black holes might work the same way. The information does not vanish. It is encoded in the Hawking radiation in such a complicated way that it looks random. But with perfect knowledge of every particle, you could in principle reconstruct everything that fell in. This would save quantum mechanics. Information would be preserved. But it would also mean that black holes behave in a far more complicated way than we thought. Other physicists have proposed different solutions. Some believe the information is stored on the event horizon itself, as we discussed with the holographic principle. The interior of the black hole might not even exist as a real place. It might be an illusion, a hologram projected from the surface. Others think the information escapes through wormholes. Perhaps every particle that falls into a black hole becomes entangled with a particle in the Hawking radiation. These entangled pairs might be connected by tiny wormholes, allowing information to leak out. And some physicists believe the answer involves new physics we have not discovered yet, a theory of quantum gravity that unites relativity with quantum mechanics in a way we do not currently understand. This theory might reveal that singularities do not exist, that space and time behave differently at the smallest scales, that black holes are not quite what we think they are. One promising approach is called string theory. String theory proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. Different vibrations of these strings create different particles. An electron is one pattern of vibration. A quark is another. A photon is yet another. In string theory, black holes can be modelled as collections of strings wound up in complicated ways. And when you calculate what happens to information in these models, you find that it is preserved. The information is stored in the configuration of the strings. String theory also predicts extra dimensions beyond the 3 of space and 1 of time that we experience. These extra dimensions are curled up so small we cannot see them, but near a black hole they might become important. Information might leak into these extra dimensions and escape in ways we have not considered. Another approach is called loop quantum gravity. This theory proposes that space itself is not smooth and continuous. At the smallest scales, space is made of discrete chunks, like pixels on a screen. These chunks are incredibly tiny, smaller than an atom by many orders of magnitude, but they exist. In loop quantum gravity, when matter collapses toward a singularity, it does not reach infinite density. Instead, it reaches a maximum density and then rebounds. The singularity is replaced by a quantum bounce. This would change everything. If singularities do not exist, then information is not destroyed at a single point. It passes through the bounce and continues into whatever lies on the other side. Perhaps another universe. Perhaps another region of our own universe. The mathematics allows for both. These theories are still being developed. None of them have been proven. We do not yet have the tools to test them directly, but they represent genuine progress. They are serious attempts to solve the deepest mysteries of black holes, and they are revealing connections between different areas of physics that no one expected. The holographic principle, for example, has implications far beyond black holes. It suggests that the entire universe might be a hologram, that the 3-dimensional space we live in might be encoded on a 2-dimensional boundary at the edge of the cosmos. This sounds like science fiction, but it emerges naturally from trying to understand black holes. It is a real idea taken seriously by physicists around the world. Let us shift now to a different question. How do supermassive black holes form? We know that stellar mass black holes form from dying stars. The process is understood. A massive star runs out of fuel, collapses, and creates a black hole. But supermassive black holes are millions or billions of times heavier than the Sun. They cannot form from a single star. No star is that massive. So how did they get so big? One possibility is that they grew slowly over billions of years. A small black hole forms from a star. It sits at the center of a galaxy, pulling in gas and dust. It merges with other black holes when galaxies collide. Slowly, over cosmic time, it accumulates mass. This process could create large black holes. But there is a problem. Astronomers have discovered supermassive black holes in the very early universe, less than 1 billion years after the Big Bang. These black holes are already enormous. They weigh billions of solar masses. But 1 billion years is not enough time for a stellar mass black hole to grow that large by slowly eating gas. The process is too slow, so these ancient supermassive black holes must have formed differently. But how? One idea is that they started big. Perhaps in the early universe, conditions were different. Giant clouds of gas might have collapsed directly into massive black holes without forming stars first. These seed black holes would already weigh thousands or even millions of solar masses. From there, they could grow to billions of solar masses in the available time. Another idea involves dark matter. Dark matter is mysterious stuff that fills the universe. We cannot see it. It does not emit light or interact with normal matter except through gravity. but we know it exists because we can see its gravitational effects. Galaxies rotate in ways that only make sense if they contain much more mass than we can see. Perhaps dark matter played a role in forming the first black holes. Dense clumps of dark matter in the early universe might have attracted normal matter, creating conditions for massive black holes to form. Or perhaps dark matter itself can collapse into black holes under the right conditions. We do not know yet. The origin of supermassive black holes remains one of the great unsolved mysteries of astronomy. Another question scientists are exploring is, what happens when black holes collide? When two black holes orbit each other, they emit gravitational waves, ripples in space-time itself. These waves carry away energy, causing the black holes to spiral closer together. Eventually, they merge into a single larger black hole. This process is violent. In the final moments before merger, the black holes are orbiting each other hundreds of times per second. They are moving at a significant fraction of the speed of light. The gravitational waves produced are so powerful they shake the fabric of space throughout the universe. We have detected these collisions. The first detection came in September 2015, when the LIGO Observatory measured gravitational waves from two black holes merging more than 1 billion light-years away. Since then, we have detected dozens of black hole mergers. Each one tells us something new. We have learned that black holes come in a wider range of sizes than we expected. We have found mergers involving black holes of unusual masses, too heavy to form from a single star, but too light to be supermassive. We have measured how fast black holes are spinning. When black holes merge, the final black hole inherits the spin of both parents in complicated ways. By measuring the gravitational waves, we can calculate how fast the final black hole is rotating. Some black holes spin close to the maximum rate allowed by physics. They are rotating so fast that their event horizons are stretched into flattened shapes, bulging at the equator. And we have confirmed once again that Einstein was right. The gravitational waves we detect match Einstein's predictions almost perfectly. General relativity, more than a century old, continues to pass every test we throw at it. But gravitational waves have opened up a new window on the universe. Before LIGO, we learned about the cosmos by collecting light. Telescopes gathered photons from distant stars and galaxies, and we analysed them to understand what was out there. Now, we can listen to the universe as well as look at it. Gravitational waves are like sound waves rippling through space-time. When black holes merge, they ring like bells, producing a characteristic pattern of waves. By listening to these sounds, we can learn about objects we could never see. Black holes do not emit light, but they do emit gravitational waves when they move or merge. In the coming years, gravitational wave astronomy will revolutionize our understanding of black holes. We will detect mergers farther away, earlier in the universe's history. We will hear black holes collide with neutron stars. We might even detect gravitational waves from the Big Bang itself. There is another frontier in black hole research that is just beginning. It involves taking better pictures. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. It was a remarkable achievement, combining data from radio telescopes around the world to create an Earth-sized virtual telescope. But that image was just the beginning. The resolution was limited. The details were blurry. We could see the general shape, the glowing ring, the dark shadow, but not much more. Future telescopes will do better. Plans are underway to add more radio telescopes to the network. Some might even be placed in space, creating a virtual telescope larger than Earth. With better images, we will be able to test general relativity more precisely. We will see the shape of the event horizon in detail. We will watch gas swirl around the black hole in real time. We will measure how the black hole's gravity distorts light. We might even be able to see the photon sphere. This is a region just outside the event horizon where light can orbit the black hole in circular paths. If you were at the photon sphere and looked sideways, you would see the back of your own head. Light from you would loop around the black hole and return to your eyes. The photon sphere creates strange visual effects. Light from the accretion disk can loop around the black hole multiple times before escaping, creating rings within rings in the image. Future telescopes might be able to resolve these rings. Each ring would tell us something about the black hole's mass, spin, and environment. And if we see something unexpected, if the rings do not match Einstein's predictions, that would be a sign of new physics. A hint that general relativity is not the complete story. There is also the possibility of discovering new types of black holes. So far, we have found stellar mass black holes and supermassive black holes. But there might be black holes of intermediate mass, weighing hundreds or thousands of solar masses. These would fill the gap between the two known types. Some candidates have been found, but they are rare and difficult to confirm. Future observations might reveal more. And then there are primordial black holes, which we discussed earlier. These hypothetical black holes would have formed in the early universe, shortly after the Big Bang. They could be any size, from microscopic to massive. If tiny primordial black holes exist, they might be all around us, invisible and undetected. They could even account for some of the dark matter in the universe. Detecting them would be challenging. They would not emit much light, and they would not have large accretion disks. But they would still produce gravitational effects. If one passed near the solar system, we might be able to detect it by watching how it bends the light from background stars. Another exotic possibility is the white hole. White holes are the time-reversed version of black holes. While a black hole only lets things in, a white hole only lets things out. Nothing can enter a white hole. Everything inside is expelled. White holes appear in the mathematics of general relativity, but we have never observed one. They may not exist in nature. If they do exist, they would be difficult to detect. A white hole would not pull things in, so it would not have an accretion disk. It would not glow. It would simply sit in space, pushing things away. Some physicists speculate that the Big Bang might have been a white hole. The explosive expansion of the universe, with all matter and energy rushing outward, matches the description of a white hole. In this view, our universe might be the interior of a white hole, emerging from a black hole in some parent cosmos. This is highly speculative, but it is a reminder that black holes might be connected to the deepest questions about the origin of the universe. Let us talk now about what black holes mean for the future of humanity. For the foreseeable future, black holes will remain distant objects. We will not travel to them. We will not harness their power. They are simply too far away. The nearest known black hole is 1,500 light-years from Earth. With our current technology, reaching it would take millions of years. Even travelling at 1% the speed of light, which we cannot yet Do would take 150,000 years, so black holes will remain objects of study, not objects of exploration. But in the far future, if humanity survives and spreads across the galaxy, black holes might become important. Advanced civilizations might use black holes as power sources, as we discussed earlier. They might drop matter into a black hole's accretion disk and capture the energy released. Some scientists have even proposed using black holes for computation. The extreme conditions near a black hole could allow for information processing at incredible speeds. Time dilation could be used to perform calculations that would take centuries in normal space, but only seconds near the event horizon. A sufficiently advanced civilization might build computers orbiting black holes, using the warped space-time to speed up their calculations. This is far beyond our current abilities, but the laws of physics allow it. There is also the tantalizing possibility of using black holes for travel. If wormholes exist and can be stabilized, they might connect distant parts of the universe. A black hole on one end, a white hole on the other, with a tunnel between them. Traveling through a wormhole would allow you to cross vast distances instantly. You could step into a black hole here and emerge from a white hole on the other side of the galaxy. But there are problems. Big problems. Wormholes, as they appear in the equations, are unstable. They collapse almost instantly. To keep one open, you would need exotic matter with negative energy. We do not know if such matter exists. We do not know how to create it. And even if you could stabilize a wormhole, the journey might not be safe. Tidal forces inside the wormhole could tear you apart. Radiation trapped in the tunnel could fry you. Still, physicists continue to study the mathematics of wormholes. Not because we can build them now, but because understanding them helps us understand the nature of space-time itself. And perhaps someday we will discover a way to make them real. Let us step back now and think about what black holes have taught us. They have taught us that the universe is stranger than common sense suggests. Time is not absolute. Space is not flat. Gravity is not just a force, but the curvature of space-time itself. They have taught us that there are places where the rules change, where the laws of physics reach their limits, where new principles are needed. They have taught us humility. Despite all our technology and knowledge, there are things we cannot observe, cannot measure, cannot reach. The universe has secrets that may remain forever hidden from us, and they have taught us to ask better questions. What is information? What is time? What is space? These seem like simple words, but black holes force us to think about them carefully, to define them precisely, to understand their limits. Black holes are also a reminder of the power of mathematics. Karl Schwarzschild discovered the mathematical description of black holes in 1916, just months after Einstein published General Relativity. But no one believed black holes were real until the 1970s. For more than 50 years, they were just equations on paper. And yet, the equations were right. When astronomers finally developed the technology to observe black holes, they found that reality matched the mathematics almost perfectly. This is one of the great mysteries of science. Why does mathematics work so well at describing the universe? Why do equations written by humans, using symbols invented by humans, predict the behavior of objects billions of light years away? We do not know. But black holes are a powerful example of this connection between mathematics and reality. There is something else black holes teach us. Something about existence itself. A black hole is defined by absence. It is not a thing. It is a place where things are not. A hole in space. A region from which nothing escapes. And yet, it has profound effects on everything around it. It bends light. It warps time. It pulls matter across vast distances. It shapes the structure of entire galaxies. Absence has power. Emptiness has meaning. This is a philosophical idea as much as a scientific one. Black holes are not just objects in the universe, they are symbols. Reminders that what is not there can be as important as what is. In many ways, black holes are the ultimate koan. A koan is a puzzle from Zen Buddhism, designed to break linear thinking and reveal deeper truths. What is the sound of one hand clapping? What was your face before you were born? Black holes ask similar questions. What happens when time stops? What lies beyond the edge of space? What does it mean for something to exist if it cannot be observed? These are not questions with simple answers. They are invitations to think deeply, to sit with uncertainty, to accept that some mysteries might never be solved. And there is peace in that, beauty in the unknown. Let us return one final time to the journey, to the experience of falling into a black hole. We've talked about the physics, the stretching, the time dilation, the event horizon, the singularity. But there is another way to think about it. Falling into a black hole is like falling into pure mystery. You are leaving behind the universe of light and information and entering a place where none of that exists. You are crossing from the known into the unknown. And once you cross, there is no return, no message you can send, no way to tell anyone what you found. In a sense, you become the mystery. You join the darkness. You become part of what cannot be known. There is something almost sacred about that, something that touches on the deepest questions of existence. What happens when we die? Where do we go? What lies beyond the boundary of life? No one knows. No one can return from that boundary to tell us. It is the ultimate event horizon. Black holes, in their own way, echo this mystery. They remind us that there are boundaries we cannot cross and still return, places beyond our reach, questions without answers. And maybe that is okay. Maybe the universe is supposed to have mysteries. Maybe not everything is meant to be known. We have reached the end of our journey. We have travelled from the distant approach, through the event horizon, into the heart of darkness. We have explored the science and the speculation, the facts and the possibilities. We have seen that black holes are real objects, described by mathematics, confirmed by observation. They exist out there in the cosmos, waiting. We have seen that black holes are mysteries, raising questions that challenge our deepest understanding of reality. They sit at the boundary of knowledge, inviting us to think harder, to look deeper, to imagine more boldly. And we have seen that black holes are beautiful, not in a visual sense, they are invisible after all, but in a deeper way. They are elegant solutions to Einstein's equations. They are windows into the nature of space-time. They are reminders of how strange and wonderful the universe truly is. If you were to fall into a black hole, you would not survive. The tidal forces would tear you apart. The singularity would crush you. From outside, you would freeze at the event horizon, fading slowly into darkness. From inside, you would cross smoothly and fall toward an inevitable end. But perhaps in some strange sense, you would also continue. Your information would be encoded on the horizon. Your particles would eventually escape as Hawking radiation, scattered across the cosmos. The atoms that made you up would join the universe again, transformed but not destroyed. And if the speculative theories are correct, perhaps you would pass through the singularity into something new. A new region of space, a new universe, a new beginning. We cannot know. The darkness keeps its secrets, but we can imagine, we can calculate, we can observe, we can wonder. And that is what science is. Not a collection of facts, but a process of exploration. A way of asking questions and searching for answers, even when the answers are difficult or incomplete. Black holes are the frontier of that exploration. They are the edge of the map, where the known ends and the unknown begins. And they will remain there, mysterious and magnificent, waiting for the next generation of scientists to ask new questions, to develop new theories, to make new discoveries. The universe is vast, it is ancient, it is strange beyond comprehension, and black holes are among its greatest wonders. So we end our journey here, floating in the darkness, looking at the stars. Somewhere out there, hidden in the shadows between the light, black holes wait. Silent, invisible, eternal. They pull at space, they bend time, they guard the deepest secrets of the cosmos, and they remind us that the universe is more than we can see, more than we can measure, more than we can fully understand. There is mystery at the heart of everything, and that mystery is beautiful. The black holes wait in their silence, the stars shine in their patterns, and we, tiny and temporary, float in the darkness, thinking, wondering, trying to understand. It is enough to know that the mystery exists, to stand at the edge of the abyss and feel its pull, to look into the darkness and know that the darkness looks back. This is the gift black holes give us. Not answers, but better questions. Not certainty, but wonder. And wonder is enough.